Morning! It is an early one this morning, so I have brought coffee with me for today. And we are going to be looking at Squeeky, the Squeaky hammer robot, which I have on the desk actually. Let's, in fact, go to that instead. I think that's a better look for right now because this is what we're talking about. This is Squeaky, the hammer robot, and there are a few problems with it, which we'll get into in half a second. But first, I think I just need to address Fast Hippie's chats here. You were very fast. Even before the stream started, you had comments in about how I want to use this hammer. I think, given the way it performed at ARC's last meet, which there will be a video about next week, this week, as in this evening, there is a video on the Melty Brain, the dual spinner vert Melty Brain, which is still a sentence I'm having trouble saying without laughing because it's kind of absurd. But I made it, and it took it to a fight, so there will be a video about that out tonight. Well, if you're watching this live. If you're watching this on the VOD, it's out already. Go and watch that, probably. Anyway, yes, we took the Squeaky hammer as well, and one of the things I found worked quite well, even though it's not there right now, is I did put a dustpan on it, and I liked having that as the mechanism for keeping the hammer down, because yes, this hammer is very, very big, and very heavy, which means that when it swings, it has a tendency to make the robot jump. So I could either like put stabilizing bars, shift the hammer around, or what I found on the day worked really well was having a dustpan, scooping them up in the dustpan, and then just hitting them a bunch with them on the dustpan. And also, the crowd loved that. Like, absolutely loved that. So that is what I want to continue on with here. Yes, physics bomb is likely a better description. For the Melty Brain, yeah, I would agree. It is a wild thing, and you will, like I said, you will see the fights this evening because it got fights. That's all I'll say about that for right now. So yes, things to do with the hammer. Now, as I mentioned, I fought this already, and the dustpan worked quite well. However, there's a couple of things that didn't quite work as well. First of all, you can see just by looking at this right now that the hammer hits the ground at an angle, which isn't the worst thing in the world, but it does mean that the sound output is reduced. Even doing this by hand, I have trouble doing it. And because it's running on a 50-1 and 20 to have enough gumption to even swing this thing in the first place, or also so that the gearbox doesn't strip out on the first hit. Because I was worried that if I put a 10-1 in here, which is what I was originally going to do, it would have just stripped the gearbox out immediately. So yeah, it's got a 50-1, which means it doesn't swing very fast. And again, the faster it swings, the more sound output we get out of this, because those are whistles in here. So the more air you get through them, the more you get out of it, which means we want to hit as hard as possible, or I guess as fast as possible, which is as hard as possible. Anyway, we want to go faster, which means a gearing stage for sure, because again, I don't think an N10 is going to be super happy swinging this big mass around. So what I'm thinking is a 10-1 N20 is going to be super happy swinging this round. So I want to do a 50-1 N20, which is what is in here, with a gearing stage to bring it down to 20-1 or something along those lines. I don't really know exactly how far down I want to go right now. I think we're just going to mess around with some gears in Fusion and see what we can do, and move on from there. So yeah, that's the first issue, is that I want to have a gear drive, and the second issue is that I want it to hit flat. Because, yeah, at the moment, it hitting at an angle means that, again, it doesn't get good, like, squeaky compression, so it doesn't get good squeaks. And that's the whole point of this thing. I mean, it does squeak a little bit, but once it's inside the big Lexan box to fight in, you can barely hear it from outside. And the few times during the event, which, again, there will be a fight on this, fight report on this next week, but the few times that it did actually make noise was when it was up in the air and fell over backwards and the hammer hit flat with the weight of the robot behind it, so it was moving faster than when the N20 was swinging it. So, I mean, sorry, that's the good audible noises. There was a couple of times I got a little bit of noise, like audible outside the box, just by swinging it, but I was having to go really, really quickly with my stick, which, look, is possible to do. It's a thing I can do. It's just, yeah. It would be nice to be able to do that more reliably and more consistently. So that's what we're working on today, basically. If you mount it further back, you'll have a better angle. Yes, so further back and higher up are the two things I want to do here. I want to move it in both of those directions. Keep the motor mounted where it is, I think, because when you throw the hammer, it pops up. So if we put more weight in the front, it will help with that issue effectively. So let's go back to the CAD. This here is the current state of the CAD. Look at the state of it. It is a little bit messy because part of this is actually the old hammer bot that was designed a long time ago now, that ended up being a lifter and then ended up becoming Run For It, the four-wheel drive lifter flipper thing that I have. The motor may have to be positioned higher. No, I think the motor is actually going to be lower and forward. So as mentioned, I want to run an extra gear stage in this, and I want to run it so that the hammer speeds up, which means that a bigger gear on the motor and a smaller gear on the weapon, so I can push the motor forwards and down and the motor back and up, and then have a gear stage kind of bridge that gap. Hopefully. We're about to try and find out, effectively, is the answer to that. So there's a lot of stuff in here, actually, that we can get rid of. So these here currently are the hammer mounts, which we don't really need. We need these. These here are the old hammer mounts. These are like the mock-ups for running a ruler and stuff on the N20 that we did last time. Yeah, that's right, because I also made this into a brushless hammer at one point. And that is just out of reach over there. I could go get it, but it would take me a minute. So let's just not for now. But I am actually going to clean up this CAD space to start with a little bit. So like this is the original Squeeky lifter design. We don't need that. We don't need a lot of this stuff. We don't need those old wedgelets because I really like the kind of horned scoop that I have going at the front here. So we're going to try and keep this. Did you look at the 507 movement link? It's for auto hammer gearing? What? Okay. I don't actually know what the 507 movement link is. That's yeah, I don't know what that is. If you have something I can look at, I will have a look at it. Probably not on stream, but maybe off stream. And it might be for a potential version 3 of this because, like I said, I've got an idea of in my head of what I want. So I'm gonna go with that for now, and we'll see where we move on to after this, maybe. All right. So this here is the main chassis. I mean, this is the old chassis. This here is the main chassis. And what you can see behind it is a representation of the hammer. The hammer is massive in comparison to the robot. I mean, let's just go back over here, and we can see that if I like throw some calipers around this thing, it's like 150 millimeters long with a little bit of compression on the hammer. And what did I measure? I measured, I think, the roundest point of the... Yeah, so about 80 millimeters. There we go. 80 millimeters around... it's hard to do all of this on camera, but yes, about 80 millimeters around the kind of largest point on these flexible splines here. So, also, actually, while we're here... 507 movements, old text and mechanical engineering. Yes. I saw that a long time ago. I haven't looked at it in a while. I probably should go back to it and see what I can see in there that would make some interesting hammer designs. It would be cool to like run this hammer in such a way that I can just run a motor like forwards and it just keeps firing the hammer over and over again. I know linkages like that exist. I just haven't ever built one, so I think I'm going to run with the simple gearing stages for this time round, and then I will in my own time have a look at 507 movements, and maybe for a version 3 we'll find a really cool movement that will just slam the hammer over and over and over again. Yeah, that'd be great. I'd love something like that, because then I could just like hit a switch and have the hammer go duk 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 duk. It should be awesome. The auto hammer is 216, but there are some amazing ideas in there. Okay, I will keep an eye out for 216 for sure. Now, the thing I wanted to do was this guy. So again, I want to hit the ground flat, but that means I want to hit the ground. So I want to have the compressed form be flat on the ground, I think, because that's where I want the hammer to end up. But if all right, let's see if I can. This is going to be interesting. How? It does hit the ground at an angle if I want it to be compressed when it hits the ground flat. Okay. But what I want to do, though, is 216, it's the same design you see in those old sprinklers. Okay. Yeah. Interesting. It can go back and forth. Yeah, that sounds like what we want. But yes, what I'm going to do right now is I'm going to compress this down as much as I can and work out where our compressed level is. So I'm going to say about 90. 90 millimeters is about our maximum compression. In fact, 95 would probably even be pretty good for the amount of compression that we want. Like, this is our maximum compression. Oh, that's the other thing I want to do here. I want to have the hammer hit the ground at the back too, because if you look at this, we're not touching the ground at all. Like, I can just in under here. So that's nothing. We want that better. Which does mean, yeah, moving the hammer axis point back and up will help with that, because that will mean that the fork here clears the chassis and allows the thing to hit the ground effectively. So let's go back into CAD. Now, I said 80 mil round and 90 mil. So radius 37. What does that get us to? 74 effectively. All right, I can deal with 74 as an estimate. But how long is this? It's probably 150, I would say. Yeah, it's 150 millimeters. Cool. So that is the full size of the hammer. Now, the other thing we need to double check. Yes, the wheels are touching the ground out here. That's good. So we have an idea of that. Now, what I want to do here? I want to do 150 minus 90. 30, so we need, 60, so we need 30. So we're going to do this and remove 30 millimeters from each side. That should put us down to our compression rate of 90. Whoops, don't do that. Measure the boy. Okay, yeah, so that's our distance of 90. So this is our hammer as it currently stands. And as you can see, so this sheet here, this is the ground plane. And as you can see, we are well below the ground plane here. We are, I don't know, 10, 15 mil below the ground plane, which means that even at full compression, if we were getting full compression, it was like at an angle compression. So yeah, I want full compression to be flat on the ground and not like this. Actually, speaking of, I did say 95, so let's just add a little bit of extra to this. So we want 2.5. Come on. 2.5, please. Right, so that'll be 95. Yes. Okay, now how do I want to do this? Yeah, I am actually going to take a copy of this, all of this, and we're going to manipulate things off a copy, I reckon. So, whoop. That'll do. Now, I do actually need a ground plate in here. Nope, go there. Cool. So this is going to make up our ground plate, Because if you just put a solid down and move it down the exact height it is, the top of it becomes the ground plate. So this is now our ground plate, and we will just make that a little larger so that I can actually use it. There we go. And actually, now we can work out how low below the ground the hammer was. The hammer was 27 mil below the ground. Yeah, it wasn't ever getting to that. And again, I really do want full compression off this thing. So, it is indeed hammer time. Yes. What else is being said? Hammer at the back could make your wedge more wedgy. It will also make hitting something with height. Yeah. Yeah, I mean, yes, hitting things with height does mean that the hammer's not going to squish as much, but again, if I make it so that the hammer at full squish is on the ground, I mean, look, I don't drive hammer bots all that well, so, yeah, I'm going to miss a lot, and I want it still to make noise when I miss, basically, is the thing with this. So I'm going to move this up. So that is now the hammer sitting on the ground at full compression. So again, this is our full compression hammer. It's not the full length of the hammer. The full length of the hammer is still... Oh, actually, it's not that one because I just changed it. Get some coffee in to stay awake here this morning. Now, let's see. We were at 95. Yeah, okay. Yeah, I could make that the full height of the hammer, but at this point in time, I think the compressed hammer is the thing we actually care about. Yeah. And the thing too here is I'm just going to make this floor a little bit smaller so it doesn't interfere with the other stuff I've got going on around here. Pull the floor all the way out to about there, should do. And, oh, I need this as well. So this little round piece over here is actually a weird trick for Fusion 360, not Fusion 360, 123D design here, which is I create a primitive that is round so that it's got an axis around it, and then I can manipulate things. So I can go smart rotate, which I'm not sure if you can see some of these things that are popping up here, but I can select that, and then I can select the hammer, and I can rotate the hammer as if it was rotating around our original point. And yeah, you can see here, that is not great. So we definitely need to find a new point on the design where the hammer can swing from here to here and be flat on the ground, because at the moment, that geometry does not line up at all. The other thing too that we need to make sure of is that so this here, I believe, or is it that one? I think it's this one here. This one here is the shape of our whistle zones, effectively. So we need to put this on here and get that to line up. And then make sure that's not fouling with the rest of the chassis design. So I don't know what this block was supposed to be. I'm just going to get rid of that for now. Right, okay, cool. You can see here that we don't have a lot of space between this block and the back of the chassis. This is the back of the chassis here. So let's take a look at how much space that is. Not a whole lot. 3.425. Which I think is actually thinner than the forks that I was running to hold the whistle mechanism. Yeah, these forks are 5 mil wide. So this isn't going to happen because the axle holding this is going to slam into the ground slam into the chassis. So these prongs are going to slam into the chassis before the hammer hits the ground. Am I okay with that? On the backswing, I think so, but I mean, I could notch out this back section a little bit, just kind of like create a small escapement in here that the hammer arm like slots into effectively. That could work. I mean, the other thing that this shows me too is that, yeah, our pivot doesn't need to be that long. Like, I mean, look at this whistle block. If we put the pivot here, it's not very far away from our actual whistle block. So we could really just throw, like, not much into this. Like, if I just put a 3mm hole. Oops. Come here. Go there. Yeah. So if we had that as our pivot point, I think that actually might work. So let's just take a quick look at that. So we're going to smart rotate around this face, and we're going to take the whistle block, and we're going to take the hammer, and boom. All right, let's take a look here. So 180, it does basically touch the ground on this side. However, how close are we there? What? This looks like I designed it. Look at that. That is so nicely, like, stacked in there. Oh, I'm happy with that. Hell yeah. Huh. Right, okay. That actually works out really nicely. Now, the only thing about this is that at the moment, it should be obvious from this angle. Hang on, if we just hide the rotational pivot for the motor because we don't need that anymore. From this angle, you can see that the chassis is actually angled up at the moment. Like, this is popping a wheelie. The front tips of these wedges are not touching the ground at all. Which means that this pivot point, while it is right for the hammer, it is not right for the robot itself. The robot itself needs to be angled slightly, which pushes the pivot back and up a little bit. Yeah, we can do that. I think we can do that for sure. This looks like I designed it. A hilarious moment to arrive. Yeah, a little bit. I mean, I did just, like, accidentally into a very nice piece of design. So, you know, I'm pretty happy with that as it goes. Sometimes you do things and don't expect them to work, and they work first try, and that is great. Okay, I needed to drink that coffee a little faster. It was a little cold there. Anyway, let's angle the entire chassis down, I think, work out where that needs to sit, and then angle the pivot block back with it as it moves, I think, so that I can then work out the geometries for where everything needs to be. That will then give me an idea of where the motor needs to be and how big the gearing needs to be, and then we can go over into Fusion in here and actually work on some gearing tech. But for now, yeah, I think we're going to do the chassis. So what's going to be the easiest way to do this? I think if we just take... Oh, the chassis is all in sections. This is going to take a little while to grab everything. I guess I don't need everything. I guess I just need the pivot point, this block, and these horns, effectively. No. I don't want to touch the pivot point. That's right. I want to leave the pivot point here. Oh, don't do that. All right. I want to move these horns down, see where they touch the ground, and then move the pivot point back with them so that it lines up. Yes, okay. I'm just getting my head around this. Pivot, yes, exactly. So, if we angle these... Whoa, it does not take much. Okay, 2 is too high. 3... Actually, 3 seems about right. I mean, this is very much just a guesstimation process at this point. Okay, so 3... See right here, you can see that there's just a little bit of the tip of the prong digging in. So actually we want probably about 2.8. Okay, 2.8 looks good. So let's go to 2.9. Yeah, okay, so 2.8 is probably about as good as we're going to get. I mean, and also we need to throw a dustpan in here too, so we can use up a little bit of thickness if we need to. Well, oh, okay. Hold please, because it just crashed on me. So I need to get that back open, and then we probably need to redo some stuff. Damn. Okay, so we're back, and yeah, this is where it last auto-saved. I need to save more. I forgot that 123D likes to crash, because it is old software at this point. Yeah. All right, but that's fine. If I rush through this without explaining absolutely everything that I'm doing, we can probably get back to where we were in not a lot of time at all here. So this is the compressed hammer. That needs to go up 27.5 to be on the ground, like so. Then we take our block, which makes up our whistle stack, and we add that back in where it needs to live, like so. And then what we're going to do is take another box, throw that on there, take a pivot point of 1.5 mil diameter, and throw that on there. Make sure our thing is all the way out. Okay, I think we're getting close. Also, I am actually thinking that what I might do here is I might actually just ever so slightly move this back a little bit, but not move the pivot point. Move just the hammer back, so that moves the hammer a little forwards as well, which, while it was very nicely nestled in there in the last design, I think just moving this back a little bit will have a couple of advantages for us. First of all, we hit further out. Second of all, we're going to be slightly further away from the chassis, so less notching needs to be done on the back of the chassis. And yeah, we'll hit a little bit further out too, which will be nice, I think. But again, I'm not going to touch where the pivot point was because I quite liked that. It just means that the hammer swings a little bit further. And right now, we are going to save immediately, so we're good. And we don't have to do all of this again. So we're gonna just really quickly redo our smart rotate here. So I did say minus 2.8, right? Because what I wanted to do, and we're gonna save again. What I wanted to do was measure between the tip and the ground. 0.083. Right. Yeah, that's going to be fine. We will be okay on that one, I think. Razor's saying it might require a bit more torque. Yes, however, if you look at... So this is the old Y-fork for the weapon. Like, there is quite a lot of length between where the whistle is and where the actual pivot point is. So the pivot point, radius of 5, distance of 32. So that means it's a 37 millimeters between here and there. Whereas if you look at this, if we... I'm going to need to do something else. Hang on. Let's just extend this guy out and then move it all the way through so it's got a nice reference. We can then measure between where the whistle point is and here. That's 13.5 plus 1.5 for the axle because we're changing. Like, this is a bigger hole than this is. So that's what, 15 millimeters? So we've shrunk the actual weapon arm itself down a little bit. So that is actually going to require less torque. However, gearing stage means we're going to need more torque. However, I don't think that's an issue with the N20. It is an issue for something else, but we'll talk about that in half a second after I've sorted out where all of this stuff lines up. So, as mentioned, this is that. This is where this is all going to sit. Now, we had a little bit of gap here, but I think that's fine. In practice, that amount of gap, I mean, it's going to be eaten by print inaccuracies and, floor inaccuracies and all of that kind of stuff. Morning, Andrew. Yes, I am indeed live. That is a thing. I am trying, as I do more live streams, I'm trying to change the time that I do my live streams so that, if you can't do what is Sunday evening Australian time, you can maybe do Saturday morning Australian time, whatever time that is for you where you live. I understand that time zones are a thing and a real pain in the butt. So I'll keep changing around a little bit so that everybody can maybe catch me live at some point in time. Anyway, so right now what we're going to do is we're going to get this back, and we're also going to move the pivot back at the same time. Once we've got that pivot back, we'll then build out the geometry that needs to hold that pivot in place. And then, that will mean that when the whole robot angles down, the pivot will be exactly here, which will be perfect. That is exactly what we want. Because if I just left this pivot here and modeled it directly onto the robot, it would have been off by 2.8 degrees, and the swing wouldn't have been as nice. That's what I'm telling myself anyway. We'll sort this out. And look, it will be fine. Either way, it's probably actually going to be okay. Sorry, first of all, I want to grab the pivot, I want to grab this, and then I want to do a smart rotate. Grab this face again, and go back, not 3 degrees, 2.8 degrees. Cool, so that all lines up again now, and this pivot is now exactly where it needs to be. Ignore the fact that the hammer is now off the center of the pivot. We can fix that. Oh, wait, hang on, I can't fix that. I'm going to grab a copy of this hammer mech with the pivot as it needs to exist, because that needs to remain consistent, and I need to have this hole at this point relative to the hammer. So we're just going to grab a copy of that and leave it to the side here. Although one of the things I like doing when I'm CADing in 123D Design is I like to move things by a very specific amount, so like 150, which means that if I want to move any of this geometry back across, I can move it by a set amount and it will line back up. Like moving things by 152 means that when I go to move it back, I have to guess where I moved it or how far I moved it last time I moved it, which doesn't make life easy. So we're going to make life easy for ourselves, or for myself, really. I'm just going to hide that, get it out of the way, because we'll come back to that later. But for now, we will actually move the pivot now that we've captured and we're going to maintain this specific distancing and stuff even after we do this smart rotate. We'll grab this, go back by 2.8, so make everything flat again. Right. So this is where our pivot point needs to sit, which means we now need blocks. I'm also going to get rid of that because that is a center line marker that I don't need anymore. So I guess the first question here is, how far up is this actually off the robot bed? It is almost 40 mil off the robot bed, so the whole thing needs to be much higher than that. Okay. Look, that's doable. Also, I've changed here to a 3 mil shaft. I'm not sure if this is a good idea. I had been using 10 mil aluminium tube, but I'm realizing that means I had to have like bigger standoffs and things. So I've got a weird idea for this particular 3 mil shaft that we might try out here today, and with this new robot. Yeah. All right. So what I'm going to do then is I am going to bring this in line here. Now, yes, I do have that. All right, I'm also going to hide the floor for a second because I'm going to do something a little interesting. I'll make a copy of this. This is definitely a centerline reference. Yeah, so there you go. That's a centerline reference, which means I can do this. So I've got this face here is now a centerline, and I want to get this closer to the centerline so that I can then shift it around and like make an appropriate gap for the hammer mechanism to swing through. So the easiest way for me to do that in 123D is to align those two here. And now that block has been pulled directly into the center line. And what did I use for thickness for the hammer arm last time? We went 5 mil on our thickness for the hammer arm last time. Okay, so I want this block to move back out. I think we're going to do 4. Actually, no, let's do a full 5. So that gives us a 10 mil gap, which means that I can do a weapon pulley and then, a weapon gear, and then also have space to have the hammer mech swing outside the weapon. I think that might be the play here. Right. So now what we've got is this. I'm just gonna shrinkify this boy. So that's 20 mil. Yeah, we don't need 20 mil on that. Let's grab hold of these. That's 4 mil, that's 5 mil. So we were, what did I say? 5. So what's this? That's 6 mil. Yeah, cool. All right, so this gives you an idea at the moment of how much gap I've got. It's not a lot. But that'll do for the moment. So next thing I want to do is obviously this needs to touch the flooring down here, and it also needs to be much, much smaller than this. So we're going to just start manipulating it a bit. 5 mil thick. That should be enough. Let's give it 6 mil. In actual fact, let's give it 6 mil on most faces. Where are we at? There. Nope. Just measure that, please. 12 mil. Okay, we don't need that much. That's all right. I'm just kind of futzing with this a little bit. Now, this is the thing. Why I'm grabbing it from both sides is because I did center it on this axle. So by grabbing it from both sides, like if I measure between here and here, that's 4.5, that's 4.5. You know what? That's actually not bad. I think I'm just going to 1.5. I think I'm going to subtract 1.5 from this. So what that means is we've got a 3 mil shaft with 3 mil of material around either side of it, which I think should be enough for this. But worst case scenario, we can, if this breaks, we can do another print with a slightly larger section on it, and it'll be okay. Now, that is 3.5. These were 3, weren't they? Yes. Cool. So I just want to push that down by 0.5 mil. Not a whole mil, a 0.5 mil. So one of the things that is interesting about this software is that it gets a little bit finicky with doing 0.5 mils and things. And then we're going to round this off as well until it's perfectly domed, and then it should just be, yeah, 3 mil all the way around, which is good. I think that'll do us nicely. Now, the next thing is to start modifying the geometry down here. So, first of all, this whole motor block assembly is going to have to change, but that's going to have to change based on the gearing setup that we do, which we'll do in a second here, because I've got problems that need to be addressed with this that we will address in half a second. So for now, what I'm going to do, though, is this here is a backstop for the weapon. We don't want that. We don't really need that. The weapon can hit the ground. That's fine. So we're going to get rid of the backstop. But we do need this channel. Actually, we might need the backstop because the backstop stops wires from getting into the gearing. Yes, okay. So we'll leave that alone for the moment. But what we will do is move this all the way down to the ground. Like that. But obviously this can't just stand up there on its own like that. It's going to need some locking geometry, so we'll do some locking geometry. Actually, right now, why not? Ooh, or do I need to work out center distancing and gear sizing first? I think that might be what we do first. I want to get this motor position first, just so that I know how much space around this I have to then work out center distancing and stuff. So I want the motor to have a gear on it that is as big as possible, and then the hammer mechanism to have a gear on it that's kind of as small as possible. Get myself as good a gear ratio as I can get. So, I mean, I've got a 3mm output shaft. So actually, let's go into Fusion and start messing around with some gears, I think. Yeah, because this is going to help a little bit. It will give us an idea anyway. So I'm going to go into Utilities, into Add-ins, into Scripts and Add-ins, and where is the gear? Spur gear, the Python version. There we go. Okay. So we're doing metric, pressure angle 20, module all the way down 1.5, I think. Number of teeth, 24 sounds okay. Let's see how that goes. Gear thickness, I want... Actually, we're just going to go 10 millimeters. Hole diameter, 3 mil. Pitch diameter, 36 mil. Okay, that's a lot. Yeah, definitely want to work on gear spacing first. Agreed. That is what we're doing right now. And yes. Good morning. So, yes, moving on. Right, root filler is too large. This is always a thing. We just need to drop that to 0.7. The hammer will have to be centered. You might want to have it off-centered to allow for gears to be centered. Yeah, that is going to be an interesting thing with this. The way the arm is going to work is going to be a little bit interesting, I think. I think that the arm will have a full width gear, but then the drive is going to have, like, the motor that drives it is only going to have a half width gear, and the the hammer shaft is going to have to come out off the gear in such a way that they don't foul on each other. That's hard to explain. Hopefully we'll be able to explain it as I go through and build this out, what I'm actually looking at here. Okay, 24 teeth is apparently a lot because it's a pitch diameter of 36. I want to pull this down real close. Let's try and go to about 12, I think. So let's go 6 teeth. No, 10 teeth? That's 15. That's all right. Let's take a look at what that gear actually looks like. Okay, there's really not a lot of meat to this gear, huh? Sure. That could be okay, though. That was 10 teeth. Yeah, spur gear, 10 tooth. I just... Out of curiosity, for my own sake, I'm going to make a gear. Also, actually, very quickly. So there was a very quick discussion of torque before, about how much torque was going to be needed to swing this hammer. And you're right, there is going to be a lot of torque needed to swing this hammer. Even this one at the moment is a little bit suspect, mostly because this printed arm is literally just ABS, and I am pretty sure that the D shaft that I've printed into this is starting to round out. And I know that increasing the torque, which is what I'm doing by adding gears to it, is going to increase the torque on this and make it break. So what I've got here is a tiny little ABS injection molded gear, there we go, which has a D shaft injection molded into it. This D shaft should be way more solid than the D shaft that I have in my other, like in my prints or in any print. And also I can probably drill and tap this with a 3mm grub screw to give it just that little bit more holding power. And I only say that because, do I have a spare N20 floating around? I should do. Oh, I do, but it doesn't have a D shaft output on it. Okay, that's not great for the this particular discussion, but yes. These are slightly not a snug fit on the shaft. They do slide on. So I think a grub screw to retain it is probably going to be a good idea. As much as I don't like grub screws, I feel like a grub screw at this size is probably actually going to be somewhat okay, or at least help a little bit. I don't know. I guess we'll find out. Why we're here is to measure this so that I know what the hole in our drive gear needs to be. Okay, 8.2, 8.3. So if we made that 8.4, 8.5, it would be a snug fit off the printer to just like squish that in place, I think. So let's do that. Back to Fusion to make our new gear, which again, we're going into utilities, no, into add-ins. Here we go. Now, the good thing about the spur gear thing is that the module stays the same. So all I'm going to do this time is jump the number of teeth up to 50, because I feel like if we do a 5-to-1 invert here, that takes our 50-to-1 gear ratio on our N20 back down to a 10-to-1. That's going to be wildly fast, and that's going to be really cool. So I said 8.5 for our hole diameter in the center. Let's just take a look at what this even... Whoa, okay. Yeah, I don't think we're going to fit this. So one way to find out here is let's take a look at our pitch diameters. So our pitch diameter here is 75, and our pitch diameter here is 15. So together, 80, 90 millimeters. That's a lot, and I don't think we have the space for that in here. In actual fact, let's just put a block there and go between here and there. That's, yeah, no, we don't have space for this. Not at all. I mean, our center to center on having the motor all the way down here. Let's take a look. What is our center to center on that? Distance 23 and a half plus 10. 34 mil, and that's about as far away from each other as I can possibly get these and still have a big gear on the motor. Also, yeah, in Fusion, what was out? It was a 75 diameter, a 37.5 radius. Let's go back into here and delete this and actually make that 37.5. Oh, that's a gear. That's... Yeah, no. That's a gear. I mean, it's a gear to rival the hammer. Yeah. Yeah, no, we we definitely can't do that. We can't have a gear bigger than the robot in the design. Okay. So let's turn off the 50-tooth spur gear. Let's find something slightly more sensible to put in here. And when we finally get to the build video for Squeak V2 and you see the tiny gear that gets printed, you all know. You all know the big gear that could have been. Let's halve this. Let's go, well, whoop. Oh, it did actually halve it. Well, kind of. It went down to 30. That's looking more respectable. I didn't actually get to see what the pitch diameter was on it. I would have liked to see that. Pitch diameter of 45. You know what? That might be doable. 45, and then the other one was 15, wasn't it? So that's a distance between centers of 50 mil. Well, actually, first of all, is there a space on the robot to do that? Distance between the centers of 50 mil. So we want a radius of 50. So this is how I'm just going to very quickly work out if there's anywhere on this robot that we could even do that. No. Okay, so see, this is the distance, like the radius here The radius of this wheel is 50 mil. So that means that the center here to the outside edge here is 50 mil. So there is nowhere really on this robot that we could center the motor and have a 50 mil. Yeah. All right. Okay, so we need to reduce that. Let's actually look for something. Let's do it this way, I think. Now that I've got this circle that shows me distance between centers, let's grab here and push until the motor sits in a place that it actually might feasibly sit. So, okay, we could maybe throw something there. So what is that distance between centers? That distance between centers is 34. Oh, yikes. I don't like that. So the reason I don't like that is 34 with a small gear radius of 15 means that we can really only do that again. So we're not actually getting a lot of gear down. Which means I think that the 10-tooth spur gear is too big. We need a smaller spur gear, so we're going to start all over again. Because otherwise we're just not going to get the gear down that I want. Like, I'd love 5-to-1. That's not going to happen. So I think the lowest I want to do is 2-to-1 on this. Aren't you mixing radius and diameter? No. So because this here, this circle is not a gear. This is giving me, like, all the points around the edge here are where I can center the motor currently. Because this distance to, like, yeah, the center of this circle, the radius of this circle is the overlap. Wait, am I mixing things up? Half a second. I know how to fix this. We can do this in Fusion. So let's grab these two back. Right. So I just want to move the 30 mil gear. Let's just very, very quickly measure our things again. So that's 15, and that's 15 mil diameter, 45 mil diameter. Now, I was saying that was going to be 60 mil that would need to be moved, but it might be 30. Let's take a look. So, let's move. I was mixing those two things up. Okay, so it's 30. Right. So, yeah, okay, 30 mil. Right. Diameters and radiuses and okay. So that is actually, that means this is our distance between centers for these two gears, which give us a 3-to-1, is here. Anywhere along the edge of this circle, we can put our motor with this gearing setup here, and it will fit. And the two gears will mesh close enough. I mean, I probably could actually, let's just add in like 0.2, 0.3, just to give it a little bit of space, because you don't want the gears meshed perfectly. You want them just a little bit loose so that they actually move and you don't have to, like, lubricate them and stuff. Okay, so that is possible, and that in actual fact puts our motor up and left a little bit. Like, you can see that it's not correct on here right now, but that's fine. We can sort that out in a second. But what I want to do is say okay to that, and then I want to actually look at the very edge of these gears. This is the absolute maximum diameter, which is 48 mil, so a radius of 24. So if we put that over here, right, so this is our gear. And what I'm going to do is I'm just going to jam this into here. That is not at all what I told you to do, 123D Design. All right, let's do this a different way. Let's go that to that. So now we know those two things are centered on each other. And that is 30.3 mil. So let's move this out to 30.3 mil. Cool. So this is where this gear needs to sit, or at least somewhere around here. So let's just move this over here. Also, what I'm going to do, I'm going to make both of these. Actually, let's make them transparent differently. So this one, we want to make, where's the transparency option? Clear glass, and we're going to make it green for now. That just denotes our points between centers. Yes, and this is what I'm doing right now, is making sure that the motor gear isn't going to poke through the floor. So we're going to make this. So this is our maximum size of our motor gear, which is still pretty large. It's bigger than our wheels, which is kind of hilarious. We are also going to make this a clear glass, but we're going to make this an orange so we can denote the difference between the two. But here's the trick of this, right? So right now, this is totally fine. But we can now smart rotate. So we're going to grab this face. We're going to grab this solid. So this is our gear. And we are going to move this. Actually, what we're going to do, it's going to be so much easier to do this if we just hide a whole half of the robot. Which, yes, I know I just said a whole half. That's valid here, as it turns out. Cool. So now we can actually do this smart rotate, grab this face, grab this solid, and then we can just move this until it hits the base plate and almost comes through, because we can just knock a hole in the base plate. Okay, so that's through the base plate there. We want it to be just above that. So let's just, so where is through the base plate? Through the base plate starts at 40 degrees. So let's do 38 degrees. And that means that it's definitely not through the base plate. What it does mean, though, is it's sticking out the front here. Okay, well, this is where having that extra set of hammer mech stuff comes in valuable, because I can swing this over and see if it's going to foul with the gear, because if it fouls with the gear, then we can't do this. But if it doesn't foul with the gear, then maybe we're okay. So let's really quickly grab that, grab this. Okay, hang on, we need to grab both of those at the same time and then smart rotate them around that face. 180, please. And then this is where the trick of moving these precise distances comes in, because we can just grab these and move them back over 150. Come on, 150. Oh, yeah. Okay, we are big time hitting that gear with the hammer. Like, this is not doable. Unless the gearing stack is way over one side so that the hammer slips past it. But the hammer mech is pretty wide. Let's go to the desk. So this is our... The problem that we're facing is this whistle box hitting the gear. And it is 20 mil thick there, and much thicker up here. 27 mil up there. What is it in CAD here? Let's take a look. In CAD, I think it might not actually be correct. Yeah, it's only 12 mil, so it actually is thicker than this. Yikes. Because this would mean moving everything over in such a way that the gearing is all the way out here, like out on the edges of these teeth. effectively. We could always lower the gear ratio, but even then, we're at 3 to 1 right now, or like a 3 to 1 reduction. So 50 divided by 3, I don't know, 20 somewhere. Well, not 20. Lower than 20? Yeah, because 60 to 1 divided by 3 is 20, so it'd be 18 or something. I don't know. I'm just approximating maths now, rather than doing anything else. Moving the hammer would be easier, but it would mean that the hammer is way further out. Like, to get this to work, we'd need... How much further out would we need to be? Let's just keep moving until we're clear. Yikes. Actually, how far was that? Like 30 mil? Okay. Doable. I mean, I guess actually there's two things we can do here. So let's do this for a second, because one of the other things I can do is I can actually... So yes, poking through the bottom of the floor isn't great. However, the whole robot's at an angle, so we've got a little bit. So what I'm actually going to do is I'm going to poke this through the bottom of the floor. We're going to move the gear down even further, and we're going to leave it out the bottom of the floor, just a touch, because that should still clear, I hope. Yeah, definitely don't want to remove the curved wedges. We're leaving the curved wedges, and we're also going to put a dustpan in there. So that all of that is staying. But what I'm doing is I'm going to move this down so it pokes out the bottom here. This still shouldn't touch the ground when the wedges touch the ground, because there's an angle which I can't do, but it's an angle between here and there, and this should still clear that. So it's not going to touch the ground unless we hit a high spot in the ground. But even then, if it touches the ground, it's not a huge deal. I can just throw the hammer to move the gear and, jump it off whatever it's hitting effectively. I meant hammer right to go for the wheels, but you could lengthen. Yeah, I think lengthening is the play, and also moving the gear down. Having it stick out the bottom, I think, is going to help a little bit. All right, so let's now grab all of this and move it back. I mean, that's helped a little bit. That's meant 30 mil now. What about sticking the hammer motor behind the wheels? I could do. However, that would mean lengthening the chassis in the opposite direction, and it would mean that we would effectively have the hammer slam into the gear at the back and not hit the ground effectively. So one of the design constraints I have for this is the hammer needs to be able to hit the ground in both directions. That is just a thing that I want personally. So yeah, that's kind of a design goal at this point in time, which means that we need to do something about the hammer not hitting this gear so that it can hit the ground in both directions. Because no matter where we put this gear, the hammer is going to hit it unless I move the hammer out effectively. So I think this is the best play. Now, what I'm going to do now is I'm going to delete this old hammer because that's just in the wrong spot now. And we're going to smart rotate this over the back at our axle point where it needs to exist for the hammer mech. Okay, I think that's doable. Maybe. I mean, it's going to be a long way out. The amount of torque we're going to need here is starting to add up a little bit, I think. This could get interesting in a lot of different ways here. All right, well, that's kind of where we're at now, I think, which does mean I've got a new placement for the gear. So that would mean this is where the motor would sit. The motor sits there, which is further up and forwards than it was before. Oh, this robot's going to look ridiculous. It's going to have a big old gear and a massive standoff and... Yeah, righto. Also, we definitely need to move. So I mentioned earlier, I've got this little thing at the back here. That needs to move so that it doesn't foul the gear and so that none of the wires foul the gear either. Yeah, that's doable. That should be okay. But we're going to now move this to the bottom of the motor. If I can do that, that might be tricky to do with everything currently set up as it is. Do I try and do that manually? I don't think I try and do that manually. I think I just do that by hiding some stuff, actually. Because if we hide this wall, yeah, if we hide that wall, we can see it. So let's do that. That should have basically lined that up, although we do want to move it back a little bit. To about... actually, let's move it back to there and then see what this gap is between this and the wall that we've got here. 1.85, so let's move it back towards the wall. 1.85. 1.85. All right, so that should be touching the wall now. Wait, which wall is it touching? What is going on? Oh, I measured to the wrong wall. Okay. I think I did anyway. Let's go back here. Measure again between here. Oh, I measured at an angle. That's what it was. 1.65? Okay. Yeah, we need to be careful about this. 1.65, because we don't want this geometry in the wall because it needs to, in actual fact, we need to get, change this cutout that's in the wall as well. We can get rid of this little V on the other side because the motor shaft is going to be much, much, much higher than that now. Oh yeah, wow. That's up there now. That's... Okay, well, we need to push this down to the ground. And then we're going to need to deal with that so that the holes that need to exist in this base plate exist in this base plate and such. We're also going to need to put a motor mount in here, so we're going to need to cut into this front section so that a motor mount can sit down correctly. Wow, there's lots and lots of little bits that need to change in this design as it stands to make this work. All right, let's get rid of that. Also, with the new placing of the hammer much further back, yes, we require a lot of torque. I'm hoping the N20 is up to this task, because if it's not, then we've just made all of these changes for no real purpose, and a 1-to-1 gear ratio might actually be what we need. Yeah. In actual fact, let's actually, I'm just gonna, real quick, let's move this back over here and see what our distance is now between the hammer and the axle. 78. Ooh. Okay. What was the old one? The old one was 32. So here's the thing about that. Like, by changing the length here, not only are we increasing the amount of torque required, we're also actually increasing the speed. So that is a speed increase in and of itself. And then I'm also putting in this gearing, which is giving us a speed increase too. I could change up the gearing, like leaving this alone, leaving this as it stands exactly right now. I could change up the gearing further, which would change. So rather than a 3-to-1, do a 2-to-1. But try and keep the same center distance so I don't have to move the motor again. But that would mean a smaller gear here and a bigger gear here. All right, so what is our actual center distance between points of here and here? That is 30. So we actually need 15? No, we need a gear radius of 15, so a pitch diameter of 30. Yeah, that's a pitch diameter of 15. That's a pitch diameter of 45. All right, let's look for a pitch diameter of 30 and just see what that gets us. That would be a 1-to-1 gearing. Yeah, that would be a 1-to-1 gearing. Pitch diameter. Pitch. I'm running myself around in circles here. All right, I just want to have a look at 1-to-1 gearing, see what that gives us. So again, we're looking for a pitch diameter of, it's gonna be 10 teeth, right? No, we're looking for a pitch diameter of 30, which will be 20 teeth. Yeah. Okay, so this is 1-to-1 gearing. Let's turn off these other two. This would give us 1-to-1 gearing with the same pitch diameter. And 1-to-1 gearing with a longer hammer is going to mean faster swings anyway. All right, and we've got a radius of 16.5. Let's go back in here. And if we change this, so what is this right now? This is 24. Actually, I'm going to copy this and just leave it as an option. Let's go 200. There we go. Now I want to turn 24 into 16.5. Where did I put my little calculator? It's morning. Maths is not happening right now. As you can clearly see. Wait, what? 24 minus 16.5. 7.5. Okay, that sounds about right. So there you go, in 7.5. Okay, I mean that. Here's the weird thing about this, is that shrinking the gearing system down means being able to shrink the arm back down, which means reducing the speed, which is what I don't want. I want fast hammer. Fast hammer. Okay, this is one of those, like, moments where there's many, many, many ways to skin this cat, and yeah, both of them kind of interplay with each other. If I increase the gearing, if I change the gearing ratio, I need to increase the arm length. So as I'm increasing the gearing, I'm getting more speed, but I'm also getting even more speed because I need to change where the hammer is to make the gearing work. And if I shrink the gears to shrink the gear ratio because the hammer's in the right spot, then I can shrink the hammer back down a bit. And I don't really know that I want the hammer quite this far out, so I'm going to have to try and find this, like, happy point where the gearing is larger and then the hammer arm is larger. Yeah. Okay, maybe that's the play. Maybe I try and stick a hammer length consistently. All right, so let's try and work out where this needs to be then. So that's 78 right now. What I know is I want it larger than the old hammer arm. The old hammer arm is 35-ish. So let's just say 35. So the old... actually, wait, I'm measuring a different thing again. I was measuring here to there. 43. Okay. So that's not that much faster, actually. Because I was measuring different things. Again, Oh man, CADing in the morning. It's a fun experience here. Maths. Why? Says the guy that does maths for a living, or sometimes does maths for a living. Oh, jeez. All right. So yes, increasing the hammer arm. So this increase, what has this increase actually given us? So that's 43. So get my little. I got a little boy calculator here. We're gonna call that 43 and say that's divided by 35, which is what the old one was. So that's an increase of 1.2. So we've got, by pushing the hammer out to that distance, we've already got, without any gearing at all, we've got an increase of 1.2. Okay, so the gearing that exists on the chassis at the moment is 1-to-1 gearing. I've already got 1.2 by extending the hammer out. And the gearing that this is set up for, like the hammer length is set up for, is 3. So 3 by, actually, let's just do that on the calculator. So that gives us 3.6 total. With the increase of length in the arm and the increase in the gearing, it gives us 3.6 times the speed on the hammer that we had before. Could use the gear stacking, little gear attached to big, and then like they use up in wind-up cars. I could. That does mean taking up more space, though. But it could solve some problems. I was trying to avoid having an extra shaft in here, though. That's kind of the point a little bit, is that having an extra shaft means having an extra thing that can go wrong. Look, Razor, I'm not sure I agree with that, because effectively what I could do is so if we look at Fusion again, and we look at, like, the 10-tooth gear down here. So we've got a little 10-tooth gear. This gear, we could have a 10-tooth gear here, and then a 10-tooth gear here, and then, or like a 20-tooth gear here, and off a 10-tooth gear, and they could, like, you could basically have a second gear stack here, like down, kind of, like if we follow this down somewhere around here, I reckon. I think we could take another gearing stage on the arm that holds the hammer, and that might work. If we did a 2-to-1, then a 2-to-1, that'd be a 4-to-1. That'd be better than what we're getting currently. All right, what I'm going to do, I'm going to look at that. I am going to look at, so we've already got these catted out. We've got a 10-tooth gear, we've got a 20-tooth gear. We know what these look like. We know their pitch diameters. Or at least we can measure their pitch diameters again. So pitch diameter of this guy is 30. Pitch diameter of this guy is 15. So together that's 45, and that means what? 45 divided by 2. No, 45, please, divided by 2. 45 divided by 2. Yes, that's what I wanted. 22.5. Okay, so these need to be spaced 22.5 apart. Right. Let me just have a look again. What were you? You were a diameter of 16.5. Okay. Actually, let's just... I'm going to CAD in everything here. See what things look like actually on the robot. So, a radius of 9. So, let's grab that first. I'm going to move these out of the way for the time being. Yeah, 90 will do. So we want a radius of 9 for the little gear. Yes, radius of 9 for the little gear. Radius 9. height, we're just going to do 10. Is there enough weight available is a great question. I've got about 15 grams that I can play with. So there might need to be some chassis lightening and stuff going on here to make all of our dreams come true. But, okay, so that's our 10-tooth gear. So our 20-tooth gear is the next question. It's this one, and it is a 16.5. 16.5, and again a 10 mil height, and we're going to again throw that on here. Now I want these guys to line up, so 29 mil in, 29 mil in. Now what did I say I needed for them? I needed 22.5 mil distance between the two. So we're just going to drop this 22.5 mil. Okay, and we're running into an issue immediately. This is really far back and low. Doesn't come out the bottom, at least doesn't seem to. Yeah, no, there's space there. Okay, and then what if we do this? We grab this. Yeah, so we need to do, again, so we're going to grab that. I'm going to make a copy of that, stick that copy on here, and then grab another copy of this, move this back 10 mil, and then across 22.5. Okay, so this is what our gearing stack up would need to be to do two. And I mean, the thicknesses of this are incorrect. I'm just mocking these up. But this is what the gearing stack up would need to look like to have two sets of gears in here that are 2-to-1 and a 2-to-1. That gives us a 4-to-1. And then actually, what I'm going to quickly do is I'm going to grab this and shift this all the way back over here. Okay, so we can see the reduction in diameter needed. Good morning, the Rook. We are CADing up a new version of the Squeeky hammer to hopefully make it swing faster. Yeah, so here we go. You can see that the reduction in diameter that we get between, and so this was the 3-to-1 gear, and this is a set of 4-to-1 gears. So, that's interesting. See, here's the thing. I was trying to get this CAD done today, like have it done today, so that I could turn around. And in actual fact, Ash was in chat earlier. I am talking to Ash at a local 3D printing company to sponsor some filament and stuff for the channel. He is 3D Printworks here in Adelaide. He's actually a really cool dude and got some great stuff in his shop. So I was going to try and turn around and have Ash print the chassis for me today. I think this may not be the way to go, because I might need to actually print up a couple of tests myself to see how fast I actually want the hammer to swing and how the hammer is going to swing. Do I have options for the gearbox on the N20? Yes, I have 50-to-1s, 30-to-1s, and 10-to-1s. However, I don't want to run this just on a 10-to-1 because I have a feeling that it's going to break the 10-to-1. So, I mean, actually, I could. That is a thought. So, we've got a 50-to-1 gearbox, and we're dropping it by 4. So what is that? So 50 divided by 4 is a 12.5-to-1. So what I could actually do is take the 10-to-1 and gear it the other way. Make the output on the hammer slower than the 10-to-1. Or I guess I could do a 30-to-1 and drop it just by half. Do I have 30-to-1s anymore? That's a question. I might need to buy some 30 to 1s. I know I've got a ton of 50 to 1s. 50 to 1s are no problem. I bought them in bulk a while back. I'm not sure if I've got 30 to 1s just sitting around that I could use. I'd have to buy some, I think. Because I think the 30 to 1s I have are either DF Robot ones, which this is going on a Malinky because it's that's just the way to it works. Or yeah, buy a 30 to 1, or I think I've got some 30 to 1s in drives for various robots, but I want to keep them as the drives for those robots. I guess 30 to 1 gear down by half is way more doable. Like, that's way more doable. Have a big gear on the hammer shaft would be nice, though, as you'd not hit it with the hammer. That's true. That's very true. However, 30 to 1 gear down by half. Just thinking about that. So, hang on. Like, these are 2 gear down by half stages here, right? This is what I was working on, was 50 to 1 geared down by 4 gives us a 12.5 to 1. 30 to 1 geared down by a half gives us 15 to 1, which is not quite the same, but it's still a vast improvement on hammer speed of 50 to 1. So, this is a 2 to 1 gear ratio. Let's move this boy back out of the way. Because what I'm thinking is that this 2 to 1 gear ratio is way easier to fit in this chassis. Like, if I actually, again, I'm going to move these out of the way just for now. That's a 2 to 1 gear ratio that we'll maybe use later, or maybe not, because I think I think we may have fixed this problem. So here's the thing. This is the way the gears are currently set up. That's a 10, that's a 20, that's a 2 to 1 gear ratio. And if we smart rotate this, grab this face, and then grab this solid, we can put that... Hell, we can put that there. We can put it directly under the mount here. Like, it literally doesn't touch the ground. So if I just do 0 again, you can see that it does not, like, there's a gap of 2 millimeters. That's sad. I'm just seeing in chat here, Pause is not using a squeaky hammer at tomorrow's NRL. Oh. Then again, knowing Pause, you've done something else with Pause, because I know Pause started as a Stampy boy and now it was a hammer boy. So what's the new ridiculous hammer attachment that you've got going on? Please tell me it's something ridiculous. But also, I kind of, and this is an idea that you can maybe take away with you. At some point, I'd love to see somebody hit people with googly eyes. I don't know how you do it, but I'd love to see somebody do it. Hit somebody with googly eyes would be hilarious. Like a hammer with the face of the hammer be a googly eye. Bam! Although, you need to call that robot, I've got my eye on you, or something equally ridiculous. Yes, anyway, weird semi-rant aside about possible future ridiculousness. Yeah, a 2 to 1, look at this. A 2 to 1 fits in the chassis without any modification, and the gear is directly below the hammer, which means that even if the width of the hammer mechanism is all the way, so like if so what is this diameter again? That diameter is 18 mil. So if I take a primitive and make it 19 by 19, 18 by 18 by 18, and slap that on there. Oh, actually, and then reduce it by 10, by 8, and go out. Okay, it would need to be thinner, but that's fine. How thin was this? That was 13 mil. Okay, we can go down a little bit lower than that. This is 18, so let's take off 6, 3. Yeah, and so, like I said, the hammer is designed... It's going to have a bouquet of flowers! Yes! I love that. That is beautiful. Yes, perfect. I love what you're doing. And at some point, I'd love to get over to NHRL and fight at Norwalk. That would be incredible. The only thing that is kind of worrying for me about that is that, like, I'm not sure if June's Norwalk has opened up yet or not, but, like, if I booked flights after Norwalk opens their registration, I'm going to be paying through the nose for flights to get to Norwalk. So, yeah, I need to kind of find a way to square that in some way. Yeah. I don't know. It's a thing. It's interesting and difficult to get to Norwalk as an international competitor. Anyway, moving back on with the design. So here we go. With the large gear below the small gear, we only need to have the hammer swing 180 degrees to hit the ground. I mean, yes, it'd be nice to be able to swing the hammer further, so that it can hit somebody that's underneath us, although the dustpan will be in the way, so maybe we won't be able to hit somebody underneath us. But you can see here that even with this set up as it is, like, this is not too bad. This is a 12 mil thick hammer arm. Come on, give me the thickness. Yeah, that's a 12 mil thick hammer arm, which, that way. There you go. Now you can maybe see that. So this is a 12 mil thick hammer arm, and our actual maximum here, so let's do a smart rotate and grab that face and grab this solid. So our maximum is, that's touching there. Right? Oh, so this is weird, because you need to look at this at this connection point here, right? So this is the edge of the gear. So this point here is the point that we'll touch first. So that is that point there. That's -9. So we add 9 to whatever this number is. It's about there. So that's 188. So 188 plus 9 is 197 degrees. So that, honestly, is pretty good. Yeah, that's not bad, actually, as far as a swing goes. So I think this is the play. I think we do a 30-to-1 gearbox. We do these two gear stacks so that we do a 10-to-1 reduction and get a 15-to-1 on the hammer. And then we can shrink the hammer back down again. We don't need the super overlong hammer again. We can use the shorter version of the hammer because we're not interfering with gears anymore. Razor saying it will cost thousands and take about 2 days to get there. Yeah, it will. I did have a look at it, and yeah, flying into New York is long from Australia. It always means like a hop to Texas and then a hop across. You can't really go direct from Australia. And the hop to Texas is 15 hours of flying, and then from Texas across to New York. It's longer, it's not longer, it's like 3 hours or something. So that's 18 hours in the air already, and then there'll be layovers and stuff. I mean, the good thing about it is time travel happens, so that if I take off from Australia, like you go from Adelaide, go from Adelaide to, I think it's Sydney, then Sydney to Houston, and you land in Houston before you leave Adelaide on the same day and everything. Like, you can leave at 10 a.m. here and arrive over there at 9 a.m. on the same day. Time travel! It's amazing! But then, of course, that does mean on the way back, you lose a day, just entirely. Like, you just drop an entire day out of the calendar. Yeah. It's an interesting time when you travel internationally as an Aussie. Path safety with both bots on the first try. Tomorrow we'll get there as soon as the doors open and be ready for a very long day. 156 beetles. Damn, that is a lot of beetles. That is going to be a long day. But that's cool though. It's cool that you're attracting that many beetles. That's insane. Yeah, again, I really, really want to do this at some point, but yeah, trying to work out a way of doing that and not have it cost me, last minute flight prices would be good, basically. Right. Okay. Yeah, I'm liking this setup here. I think this setup is actually going to do what we need it to do. Now, the thing I want to do now then is to work out the hammer. Work out how long the hammer is here, and then we'll put a dustpan on it. But I still reckon that probably going to close the stream out in a little bit here after I've fixed some of this gearing up. I still reckon I'm going to do a test of this first. Like, I'm going to do a test print of the gear stack up of the hammer arm, all just in PLA, which is not really combat ready, but will do the job for a test fire. We'll get a geometry set up that we can do a test with, and I will do that test before I get this chassis printed properly, and just, make sure that it's swinging correctly, it's going to squeak when it hits the ground, like, all of those fun things that we want to see it do, basically. That does mean I will probably need to mimic the shape of the chassis. Yes, I want to mimic the shape of the chassis, so I mimic the, 2.8 degree angle that the chassis sits at when it's running on the ground. Yes, that makes sense. Okay. I've got a plan. We have a plan. Right. So let's get the hammer length going again. So for these, for the moment, actually, I'm just going to hide these for the moment. I don't think we need them right now. And I think this hammer length is going to be fine. Now, right? Oh yeah, that clears that. No worries, and hits the ground. Again, here we go. Look, so here's the big thing with this is, yes, that is the hammer is now going to sit inside the dustpan. So even if we could swing a little bit further in this direction, which, you know what, we may not be able to, because I think if we swing too much further, the corner of this is going to slam into our gear. Whatever. Doesn't matter, I don't think. Because we're going to hit the dustpan before we hit the gearing. So that's fine, I think. I think that, yeah, with the gear above, we're going to get at least 180. Hitting things on my table. With my elbow. Ow. Yeah, we're going to get at least 180 degrees of swing, even with that setup, even if we have a weapon shaft that is the full thickness of the gear and stuff. Like, I think we should be okay here. So, yeah, I think I want now to work out a way of printing a test jig for this. And also, we're going to finalize our gears. I think we're going to finalize our gears as the 10 tooth and the 20 tooth over in Fusion. Now, are these actually just straight up finalized at this point? Let's take a look. First of all, we're going to look at this guy. What's our center here? Our center here is 8.5. Perfect. That fits this little gear that I talked about earlier. Although we may need a way of retaining it. That could be interesting to do. But okay, so what did I leave myself in the chassis? I left myself, how wide is this channel in the chassis? Man, too many things going on in here right now. Actually, if we just go like that, yep, that moves that out of the way, perfect. So how wide is our channel in our chassis? I don't think it's very wide at all, to be honest. Okay, channel in the chassis is 10 mil. The hammer sits much higher than that, so we can offset the hammer one way or the other. Showed you 150 gram hijinks bar to a few people. They're excited to see how it goes. Oh, also, I realized I'm not back on the fusion thing. Whoops, my apologies. Yeah, I am also very excited to see how it goes. However, as I have a little bit of time before this month's meet where it will get fought, I am actually putting together a whole other ant weight because I'm kind of expecting Lojinx to explode on the first hit. So I'm bringing a backup robot with me. Yeah, because I'm expecting it to explode. So, yeah, there's a fun robot that I am putting together. A return of something that hasn't been fought in a little while, which some people thought was been retired, but it hasn't been retired yet because I've still got plans for it. So, but you'll see that much later. That's like 2 or 3 weeks away at this point, doing a video on that. And it'll be fun. We'll test out some new stuff that I've got access to now, and have, yeah, it should be an interesting build for that one, I think. I'm doing something with an ant weight I've never done before, which, I mean, I guess that's like half my videos now, right? Like, yeah, a lot of the times when I'm building a new ant weight or even revising an ant weight, I'm doing interesting things with them because yeah, I don't like to get stale. I like to design and rebuild and try things out and see how things work. And yeah, you all come along for the ride, which is great. Righto. So I want to make a jig for this robot. So I think what I'm going to do, so I'm going to leave this geometry set up. Now, oh, that's right. That's what I was going to do. I was going to look at this. So this is 10 mil thick, right? Nope, that's not what I wanted you to do. Let's just measure down the side. Yes, that's 10 mil thick. So that's the exact width I've got in the chassis. I maybe don't want that, actually. Can I modify that? I think I can. If we go into the spur gear and fix the extrusion, edit the extrusion feature. Yeah, I don't want 10 mil. Let's do 8 mil. I need to modify multiple extrusion features. Okay, that's that extrusion feature. That's that extrusion feature. Okay, here we go. 8 mil. Cool. Okay, so then I was going to... Razor saying that is the Team Panic way. Yes, yes. I mean, it does often lead to me panicking about things, hence the team name. But yeah, that's fine. That's fine. We sort things out. We get things done most of the time. I wanted to now double check how far this is. I'm just going to very quickly move this central pillar down so that it has a face that interfaces with this centerline face. And that's 5 mil out. Okay, so that is straight up 10 mil. Yeah, okay, that's 10 mil out. Right, so... How do I want to do that, then? Because I was trying to have the gears offset. So I was trying to have it so that if we go back into Fusion... and we look at this... go back into the full gear stack up. So I was trying to have it done so that these two gears meshed at 8 mil, and then the actual like hammer arm came off here, which I'm not sure if you can really see what I'm saying here. Let's just go back here, create a sketch on capture positions. So this is our plane. I was hoping to kind of do, like have the hammer arm here, but obviously have it like that or something, so that the gear and the hammer arm didn't like interact in any way. But again, I think the geometry lines up so that we can just do that. I think we can just have them in line. I think that's also going to make my life so much easier. So I think that's what we're going to do. Although yes, I'm going to... Well, that's not what I wanted to do. I was showing you my desktop. There we go. We are going to move these back a little bit, maybe 2 mil, just to give me a little bit of space and let me run a full width 10 mil gear here. I also want to just delete that sketch because I don't need it. Delete sketch. Yeah. So we're gonna have a full width arm effectively, and also I'm going to get rid of this, and we're going to make a new component, which is going to be hammer arm. Okay. So now we've got hammer arm, and we're going to make a new sketch. We're going to project include the entire gear. So that's cool. Then I want to work out. So I was going to use this distance between axle point and squeak, or squeak a bit, which is 13.5 plus 1.5, 15. Cool. So we're going to go and do a line that is 15 mil long. 15. Right, okay, so that barely sticks out past the gear, actually, which is kind of okay. I'm all right with that. Turn that into a construction line. Then how thick are we doing this? Probably the same as we did last time. Oh, that's right. We're going to do... Oh, yeah, we'll do 13. We'll do... No, we'll do 12. I feel like 12 is good. So let's offset this by 6. And then offset by 6. In the other direction. Oops. -6. So this makes up where we want our squeak mechanism to land. Now this interacts down to this tooth here. Just thinking about how I want to do this. I think that's fine as is. I could like chamfer in here and have it connect. That does create a smaller cross-sectional area though, which I'm not sure I like. Let's just, if I just do between here and here, what is the cross-section across there? 5.7 mil. Yeah. Okay. I don't love that as a cross-sectional area. Like, that's 5.7 mil that's carrying the entire speed and weight and everything of this hammer. I'm much happier with 12 mil cross-section to carry that. So we are just going to use, yeah, this entire section here. Now, from here, we need to work out what this shape does. So the width down here is 26. So in Fusion, we're just going to do a line of 13. This is, I've just thought of a thing, but that's fine. We'll just keep going with this. So we're going to mirror this across there. And then I want, how tall are these? These are 35 mil tall. So in Fusion, we're going to go line up 35 mil. And that is going to be a construction line. And then what was the width of these? 37. Wait, did I mess up in Fusion here? I did, I think. Oh no, 26 halved is indeed 13. 37 halved is something different. Obviously. Whoops, no. 37 divided 2. 18.5, okay. So then in here, we do 18.5. And again, do a construction line. And this time, we connect these. Boop. Just like that. And in actual fact, this and this can be construction lines as well. In fact, I'm going to delete that, I reckon. Because then we'll take all of this at the same time and flip it across. Like so. So this is one mirror operation because, I don't know, Fusion gets a bit weird about mirror operations. If you do too many differing mirror operations, at least for me, it starts to slow the computer down a lot and starts to slow down computation times and things. Like even now, that took a second to get all of that mirroring done. And I don't understand why. That feels a bit weird to me. Anyway, this is our squeaker box. So this is the thing that we want to try and capture. And the last design, I used 5mm thick. Yeah, 5mm thick. Oh, that's going to be interesting. Because how much space do we actually have? Well, one way to find out. Let's offset this by 5mm. Minus 5mm. Yeah, that's getting real close to that gear. Well, this is why we're going to do a test of this, I reckon. And again, we're going to offset this by 5, but minus 5. Oh, and I do need these lines to not be construction lines. Okay. Well, I need that line and that line and that line and that line. Oh, actually, what I'm going to do, because I think if I look at this, this is the final output. Yeah, length 25.487, because I've added in the tolerances needed for 3D printing. So we're going to do that here with the offset function. So we're going to do an offset of, oh, that's offset in the correct direction, but we're going to do an offset of 0.3. That'll give us a solid line that gives us a little bit of 3D printing tolerance, effectively. And again, we're going to offset this line, but this time minus 0.3. That again gives us that line. Now, I've just realized I've got extra lines that I don't need, so we're going to get rid of those. Cool, and then I don't need this fork to be this long either. So at the moment it's wrapping around the top of the squeaking section, which is too long. We do not need that. So let's just try and quickly, if we can, work out approximately how long these are. Distance 30, so probably about 25. Oh, actually, here's an easier way to do that. Throw it in a box, snap it to there. Then that gives us a good reference to reference against. It's exactly 30mm long. Okay, that's fine. So that does mean, literally what we want to do is we just want to do a line from here to here that is horizontal. And then distance that. I mean, I could have done this a million different ways. I could have created a point on a line and done the mirroring trick again, but as mentioned, you know, mirroring in Fusion gets a little bit funny. But yeah, there we go. This is our little our current setup for how this needs to work effectively. Now, just gonna double check that I was correct on all of my measurements here before we commit this to an extrude. Wow, it'd be good if I could, you know, handle the software that I was using. So base of the squeak to there, 13.5 plus 1.5 for the diameter of the thing is 15 exactly. Into Fusion. And I'm pretty sure this is 15 exactly. Between here and there. Of course, that's 14.7 because of the offset. Right. Well, I should have somewhere around a dimension for this line, and if I don't, we can get a dimension for that line. Oh, save. Yeah, good call. Let's save that, and also let's save fusion too, just in case. User saved, no worries. So I want to dimension this line. That is... okay, so there is a dimension for it somewhere on this page, but... look, actually, it's going to be fine. We'll be right. We'll be fine with how this is. So I think we're actually good now. We can finish this sketch. Is there a system I can recommend that is sort of plug and play system electronics for ant weights, beta weights? Unfortunately, no. The closest thing you can get is the Malinky Nano, which is actually what is in this robot here. If I go back to the desk scene, although you can't really see it because I don't have a screwdriver nearby. Actually, do I have a screwdriver nearby? How do I not? I always have a screwdriver on this desk. I've cleaned up. The Malinky Nano is the closest you're going to get because it's a receiver, an ESC, and power distribution board all in one, effectively. So you only need to solder the battery in and the motors on, although the battery does need a switch in line. So that's minimal soldering. That is the lowest, like, soldering to entry you will have in an ant weight, and that's for an ant weight. There is nothing like that for a beta weight that currently exists, although they are working on, or at least I've seen discussion of, a high voltage Malinky Nano, which may work for beta weights. However, that'll only work for drive for beta weights, and you'll need to wire in stuff for a weapon for beta weights separately here. Yeah, if you haven't seen Malinky Nano, look at the Malinky Nano. Definitely the easiest way into the sport currently in an ant weight. All right, we're going to finish this up, and we are going to do a 10 mil extrude on everything we want in the design, which is all of this. Okay. Yeah, so that is going to be our new hammer arm. Looks kind of wild. Kind of like it. Although I might round some corners off here, actually. Can't round this one too much because the more I round it, the less material is holding the hammer together. But I can round these boys in here. So let's fillet these. At least a little. Give them a 2 mil fillet. That'll be fine. Let's fillet these outer edges as well. Nope, not that. This and this. Again, I'm just going to do very little here because, again, the more I do here, the more weight gets taken out of the thing. I can't fillet these corners because they need to hold square corners of the hammer. So that'll be okay. Could I fillet these top ones? I think I could. These aren't really doing a whole lot up here. Sure, it's a little bit of extra meat, but it's not huge. Do I like that? I think I kind of like that. Miss things. Did you go with 30-1 with a 2-1 gear ratio? Yes, that is the plan here. So this new hammer arm has the 10-tooth spur gear on it. You can see if I open the 10-tooth spur gear, they are effectively the same thing. And then I'm going to put a 20-tooth on the motor output. So it's a 2-1, which takes our 30-1 gearbox and brings it back into a 15-1. And that is going to be way faster. It's going to be real good. I am very, very keen and excited for that to happen. I think, though, we are actually on a shorter weapon arm, though, than we were before. Because, yeah, this one's at like 30. That's a point. That's a good point. We've got a shorter weapon arm again. This is why I'm going to do testing. I've got I've got this design. I can modify this around a bit, and I can change where the weapon arm sits, and I'm going to do that to work out how far things need to be and how I want them to be. Because, yeah, this is about 35. The new one's about 15. So that's a reduction of 2 to 1, which means that we're effectively getting the same thing as if I just jammed a 30 to 1 motor in there, because I've got the 2 to 1 gearing down, and then I'm getting it back again with the length of the arm. Gearing is a pain. Especially gearing here is a pain, apparently. But, I mean, the thing about this is I don't want to mount a 30 to 1 motor all the way up here. That just feels like weight in weird areas. Weapon arm is definitely the best way to tune it, I think. So yeah, we'll be doing some prints. I'll print a test chassis that has everything where it needs to be, and then we'll work on an arm length. And then once I've got all that locked in, I'll lock the chassis in, and we'll get a really cool, good print from 3D Printworks for the final version, which, yeah, needs to be done for the end of the month. So we've got some time. I've got some time to mess around with this and adjust gearing ratios and all that kind of stuff. And also, gives me a little bit to put in the video for version 2 here. We can look at together on that video some different gearing ratios and get that all going and sussed out. U3 Cubing says, I made a 1 pound outweight just by putting a shell and wedge around one of those 2 sides, flipping cars, no soldering. I kind of feel limited what I can do. It's too bad there's no wire plug-in system. Yeah. Unfortunately, the problem with a wire plug-in system here is that most robots are fairly unique in terms of build layout. Yeah, and what I mean by that is, like, this robot, you know, the wheels are this far apart and this point on the design. And so, like, if I designed a PCB that I soldered together that had the motors this far apart, I could sell that as a run plug-and-play system. But if you suddenly wanted to run a horizontal with a wider wheelbase so that you could turn properly, then my plug-and-play system falls over and you can't use it for that. This system, like, this works for this exact wheelbase and wheel length and stuff, but having the motors soldered directly to a board already, yeah, means that you've kind of locked them in place. Or somebody has to solder them on a length of wire, and then you've got a length of wire that you have to deal with, which means that either that wire ends up coiled around in your robot because you've shrunk the wheelbase, or it's really tight because you've got a wide wheelbase that you want to use. Like, it's really, really hard to design a plug-and-play system that will work for the many thousands of ideas that people can put a robot together with effectively. Yeah. Print a crazy long arm for funds? Sure. Yeah. I mean, I've got a 30 by 30 build plate. We can get a 20 mil arm off there. Just, you know, see what happens. I mean, I'd miss entirely on the swing because it would be so far in front of the robot that it would just be ridiculous. But, you know, for funs, we can try for fun. Fingertech Viper kit. Here's the thing. I think a lot of the kit, like, even the kits have soldering in them. Like, you need, well, again, there's an issue with connecting motor wires plug and play. So the DF robot motors do that. The DF robot motors have a little connector on the back. And again, oh no, I do have them here. Here we go. Here we go. Look, I'll show you the problem with plug and play the way you're talking about. Here we go. Where's my desk? There's my desk. So here, I have an amp weight chassis. I have DF robot motors that have an ESC on the back of them. These come to a servo plug. So you can wire these directly into any standard receiver, right? But because they are making these plug and play for any size robot that could possibly use the N20 motors, these cables are ridiculously long. There is so much cable in here because they are letting these be available for people who are building really wide robots or using these as part of a servo arm, like lifter grabber type, on the desk mounted arm thing. So if I leave these as plug and play, which is what I did when I used this robot in this particular configuration, I just had to tuck a ton of wire into the chassis, which means the chassis needs to be bigger and heavier than it would have been if I had not run these wires and instead had cut them and soldered them directly to a PCB. So the inherent problems with plug and play, and I understand. I get not being able to solder, not having access to the tools and the equipment, and still wanting to get involved. I really, really, really do get that. And I wish that we could solve these problems and that a really great plug and play system could be available to people, but it's just a very, very difficult problem to solve when what you're attempting to try and do is create a plug and play system that needs to work for so many designs. And it's the problem with that is that you can only sell a plug and play kit like that to ground level beginners, because the second that you do something like add lots of wire because you want people to have the flexibility to put their motors wherever they want, then the advanced people are not going to buy your system anymore because all of this wire is extra weight and space that they don't want or need in their design. And so your market shrinks considerably. It's just a very, very hard proposition. And look, personally, I really, really wish that there was a way to do a plug and play system well. And if there was, I would do it. But unfortunately, I can't think of one. And a lot of people haven't been able to think of one. There's lots of people in the sport who would love to get more new people in, but it's a hard proposition. I will say, while soldering can be intimidating, it is a valuable skill to have. And soldering irons, even cheap, dodgy soldering irons from like your local hardware store that you pick up for $5 that doesn't have a temperature regulator, will do the job. It's a valuable skill to learn if you can and have the ability to do that. Again, I understand that not everybody has the tools, not everybody can afford to buy the tools needed for this. And again, I really, really wish we could build a plug and play system, but unfortunately, it's just not that viable, given the way combat robots kind of go here. It's just, it is the kind of the unfortunate truth of the matter. Look, there are, and like I said, like it has been said a couple of times, there are kits that are available. A lot of the kits that are available are low to no soldering, or I would say low soldering. And those type of things may be the way to go, is go for a low soldering thing. Main reason for me not soldering is for health. Yeah, okay. I can understand that. I mean, soldering, it does need to be done in a well-ventilated area. You should be soldering with lead-free solder. I say that as a person who does solder with leaded solder, because leaded solder just makes life a little bit easier, unfortunately, but it isn't great for health. That is very true. That's... That is a tricky one. I don't know how you can really get around that. Lead-free solder does exist. It is harder to solder with, from my own personal experience. Although, having said that, my last experience with lead-free solder was 10 years ago, so it might be better now. But it certainly was not good when it first came out, or when I first started using it anyway, and then very quickly stopped soon after that. No, that's fine. I really like helping out, and I like trying to get new people in and, helping as much as I can on this type of thing. It's just, unfortunately, sometimes, I can't. That yeah. And that's kind of where we're at here, is that there's not much that can be done without any soldering at all, that doesn't involve, this type of thing. Yeah. Having said that, I mean, the DF robot stuff might maybe be a way to go, because, again, you can connect these directly to a receiver. The only thing you would need to do then would be to find a way to connect your battery through a switch into the receiver. And maybe people like Bristol bot builders might know, or might have some kind of like wiring harness set up already that's got the switch and the battery connector and stuff ready to go. Maybe, I don't know. That might that might be a thing that could be done. Wacky Ninja, lead-free tin solder is still difficult to use, can confirm. Okay. Yeah. Yeah, understandable. 3D Cubing saying multiple length wires. Yes. But again, you kind of run into this problem of economy of scale things, right? Like, the more you have different size cables, that's more products that you're offering, which means you have smaller market for each of those individual products. Yeah. Like, unfortunately, our hobby is very, very small. A lot of the stuff that we do is all stolen from drone stuff, right? Or like drone stuff, or RC car stuff, or, hobbyist robotics who are doing stuff like building little like grabby, sitting on the desk arms that move around and do things. So, yeah, trying to run a business to like, and you need to be able to provide stuff like this, you need to run it as a business and make a profit so that the business survives enough to keep producing product, and you have enough money in the bank to go to a factory and say, I want 1,000 of these or 10,000 of these, or whatever their minimum order quantity is. Yeah, and by doing things like offering different wire lengths, what you end up in is a kind of catch-22 point where, yeah, look, it's difficult, unfortunately. Again, it's a thing that I've been thinking about, but it is a hard thing to do. Right. So where was I? I have this set up. I do need to work out a way of, just making various different versions of this with different length hammer grabbers, because yes, that would be hilarious to run a like 200 mil one, or like a 20 centimeter one. That would be absolutely hilarious. I mean, it's gonna break things, I think, but it would be very funny. Yeah, so I think the final thing I'm going to do on stream here is we're going to very, very quickly do up the test platform that I want to do, and then I am going to end stream, because I've been streaming for a little while now. How long have we actually been streaming right now? I don't know. OBS will tell me. I've been live for 2 and a bit hours. That's fine. Team Smoky Robotics, just join what's going on. We are building a new version of the hammer ant. I have a Squeeky hammer. This guy. But the problem with it is that the pivot point is too low, so it slams the hammer at a weird angle, and it was too slow on the swing. So we're redesigning this entirely to run a gear stage, push the hammer up, and then also have the hammer hit flat on the floor to get some good squeak going. Okay, Fast Hippie mentioning some mechanical movements, 216 for auto hammer, 268 for never ending spear poker lifter thing, and And 69 is a one-tooth gear. Okay, that's interesting in a lot of different ways. All right, so what I want to do here is I want to get rid of all of the things that aren't going to be needed for the test. So in that case, this is the back, the motors, the motor mounts. Although I do need to do something about being able to have the wheels offset off the ground as high as they are currently. So I might need to like split these and make a print of them and just glue them back on again. I think that might be the best way to do that. That's our gearing. Let's get rid of these and these and these and these and these, because we don't actually need the motor that high anymore. The motor is going to go in the center of this. Oh, that's going to be interesting to do. Also, I do actually want the motor to mount to come back, because I need a motor mount in this eventually. So let's actually take a look. Our motor needs to go there, which kind of means that these mounts probably need to angle around the motor or mount on top of the motor. That could be problematic. Just thinking about that now. I do have a motor mount here. So let's just sit that on top of that. Because this could be an option. We could do this weird thing where we glue or... Actually, I think that's feasible. I think this is very feasible. I think what we're actually going to do is do this. So have the motor sit all this way back, like it needs to sit back here anyway, about 10 mil back. And then we're going to have the motor mount have the... actually, what is going on here? Why is that not... Okay, let's just copy that distance and move the motor forwards by that. There we go. So that now lines up correctly. So we can actually have the weapon mount off the top of the motor mount, and we can like glue this into the motor mount effectively, so that we can print the two things in the right orientations that they need and still actually have them joined together. And then we should be able to do that. Like, that should be good enough. I mean, I think the only thing that might be a bit weird about this is maybe like the other side will get glued in straight, and then you might need to put the weapon axle in before connecting this motor mount to make sure everything lines up correctly and sits down where it needs to. Now, before I cut this motor, this weapon mount down, I am going to mirror it about the central axis. So we've got that. We want to mirror it about here. So now we have two of those, and our gearing stack up is totally in the wrong space, but that's fine. We're just going to move these across. Actually, we don't need these to build the test platform anymore. Now that we know where the motor goes and we can see that everything sits down okay, we actually don't really need them. Cool. So actually, I'm just going to hide those for the moment. Hide. Oops, I did the wrong thing, and I've just shown all the stuff I hid before. My bad. I have been streaming a while, and I'm starting to, yeah, not be thinking about things correctly here, apparently. So now we want... Don't do that. We want to snap this to the motor, and then we want to move it. Oh, actually, this is going to be interesting. We might need to move the hammer mech forwards a little bit, which will actually mean lengthening the hammer arm again so that it doesn't hit the back. But the reason we might need to do this is so that we can fit the motor mount in for the the other motor, the drive motor at the back here. Okay, so this is 0.5 mil too far forwards. So back that off by 0.5 mil. What is going on there? There is a lot of gap between this motor mount and this. Okay, I'll have to deal with that in a minute. But for now, what I want to do is I want to grab back this and this. Come here. Control, copy those. We had to have moved that 400. But yeah, see, here we go. We've got interference between the two motor mounts. I was slightly worried about that. So the options are to move the hammer arm forwards or to move the gear forwards, can move the entire setup, everything forwards, or I can move the motor forwards and down a little bit simply by rotating. So if we show these again, we could smart rotate. Nope, that's not what I wanted to do. That. It's forwards and up. Okay. If we do that 16 degrees. Couldn't you rotate the ref and motor forwards? Yes, that is exactly what we're doing right now. I could maybe fuse the two motor mounts together. That would be interesting. Yeah, that would create a really tall motor mount over this side, but I mean, in theory, it's doable. Yeah, that'd be doable. We could change this motor mount to be one motor mount and have, like, run these 4 bolts at the back here and then run these 2 bolts at the top here, and that should compress everything together. Have the weapon motor top plate mounted. Yeah. Have you seen the top plates that I make? I don't make very sturdy top plates. I would much prefer the weapon motor to be mounted to everything else that's here. But yeah, as you wanted some weight forwards, I think, yeah, weight forwards is a good idea, really. So actually, that's what we're going to do. I've moved this forwards by 16 degrees. You can see that it moves this way a bit. Then if we again go like this and like that, that moves that forwards. And I think now we should be okay, although I might not be able to. Yes, I can. There we go. Yeah, look at that. Plenty of space. No worries. No worries at all. The only thing we have to worry about with that is whether or not we might actually still need to extend the arm. Cookie container top plates. Yeah, cooking container, bolt containers, just a bit of everything, really. Wait, yeah, hang on. I've got a thing. And then, yeah, here we go. Let's go back to the desk. So, this here is a blister pack of screws. It actually is currently got the screws in it for some brushless motors. This is a spare blister pack. It did come with some, like, M4 bolts or something in it. But this blister pack of screws comes from my local hardware store, Bunnings. And the plastic in here, specifically, this nice sheet of plastic right here, That is the armor that I've been running for my top plates for ages. Like, anytime I'm low on weight and still need to put a lid on it, it's this stuff that I have been going to. Very, very soon, though, well, actually, as of now, I am moving over to milk cartons as my top plate of choice because they're very thin HDPE, which is going to hold up a lot better. And yeah, hang on, actually, if I do this and go back to the desk, this boy that we've already been talking about on stream today, Low Drinks, has a milk carton top plate. So that should hopefully survive a little bit better than the, I think it's PET in those cartons that I just showed you. So yeah, no, we're not mounting anything to the top plate. The top plate is an afterthought that we'll deal with much, much, much later down the track. Look at that solid top plate. When your weapon system is 95 grams, yes. Yeah, no, you really can't do anything top platey when your weapon is most of the way to the robot. So, all right, we're going to move all of this back by about 2 mil. Seems to work. Okay. I will need to sort these out in CAD a little bit later so that they're nicely aligned and stuff. But yeah, that will work. That will work out quite nicely, actually. And it still gives us the ability to mount this off of here. What I think, though, is I might... All right, yes, actually, I'm going to do that. So that separation is quite nice. But what I'm going to do, I'm going to move this back by 1 degree. And I'm just going to dump all of this out here so it's not in the way and I can snap it into position in a second. Just so that the mount here lines up better with the top of this mount and so that these are a little bit closer to touching. Yes, and I do need to be careful about rotating too far forwards because then, yes, the arm can hit the gear. So we need to, yeah, rotating back a little bit is not going to hurt us here. So that's what we're going to do. We're going to go back. I know, we're going to go back 2 degrees. But also, here's the thing, though, right? Like, all we need is something that is 12 mil wide by... Let's go 12 by 12 by 10. So this, and I'm just going to go out that way, needs to get to there, which, oh, that is close currently. Okay, yeah, so that is actually a problem. Maybe we do thin out the hammer arm then. Rely on the thickness of 10 mil wide and less on the thickness of 12 mil here. Because, yeah, at the moment, that doesn't actually fit there. It has to go... Let's see, how much further up do we have to go? 7 mil. Okay, well, just under, so about 6 mil. What were the motors with those plugs called? Those are DF Robot motors. They're like, I think, so if you go to DF Robot, which is a website, they have, I think they call them micro metal gear motors with speed controller or something along those lines. If you want a... hang on, I can maybe... Let me see. Let me just... I'm just going to see if I can pull this up on stream without, like, doxing myself badly by showing you anything that I shouldn't be showing you in my web browser. Just give me half a second. Here. Not with connector. Ah, yes, micrometer gear motor with driver. That's right. So just give me half a second. I'm gonna see what I can do here. Okay, this looks to be about right. Let's go back here and go here. So these are the motors that I was talking about. So DF Robot, Gravity DC Micro Metal Gear motor with driver 50-1. That's these. These are the ones that I used for a long time and still do use in certain builds. So I either use these or I use a Malinky Nano, and these have got a 30-1 option, a 50-1 option, and a 75-1 option. So depending on the speed you want to drive at. Personally, I would say get 50-1. It's pretty average, middle of the road speed. It's fairly controllable. For a first time or second time or even fifth time robot, 50-1's pretty good. If you're ever building something where you're like, no, what I really, really need is speed, 30-1's at the go. 75-1's, just don't, basically. So yeah, that would be my recommendation here. See you later, Fast Tippy. Thank you for the stuff that you have been kind of saying in chat and the suggestions you've given. It's been good. I probably won't be streaming too much longer because it is also now lunchtime here and I'm getting real hungry. So we're gonna finish up pretty soon here, I would say. I'm just gonna finish doing what I was doing with this particular setup here, and then I think we'll call it for today's stream, because that'll be, I think we're over 2.5 hours now, which is a pretty decent length of stream, I would say. So we will get to that in half a second. But first, I'm going to finish up this little test platform and get that rocking and rolling so that I've got something to print very soon. Ah, look at that. Look at this. We've still got space. We're going to go back another one. I'm going to go back another 1 degree, I think. So let's just undo these. There we go. And go back another. Where are we? Smart rotate. Grab that face. Grab this solid. Back another 1 degree. Actually, let's go 2. And the RC world seems to have... The RC world seems to have it to a science of plug and play stuff. Really? Because, I mean, this is the thing. If there's RC gear, like, not toy stuff, like the toy stuff is, like, the toy stuff is not good enough to run in combat robots. But if there are RC motors, like for hobbyist level RC motors and gearboxes and stuff that are all plug and play and ready to go, use that for your robot. That will work. Like, robot people steal stuff, use stuff that is designed for RC hobbyists all the time, and that stuff will work. The problem you get is if you try and run RC toys too much, a lot of the RC toys, because they're built to a price point, they have plastic gears all through them. And those plastic gears strip out easily. Very, very, very easily. So they'll only last a fight or two, and you're going to have to continuously buy RC toys and strip them apart and, you know, use them that way. I did do a video on this a little while ago. There's a video on my channel that's called something like things to know before making toys into combat robots, or before hacking toys, or something along those lines. So if you're thinking about using more toys to make combat robots with, have a look at that video, because I deep dived into a bunch of things wrong with a lot of the toys that you can buy on the market, and I did recommend a few that, if you really, really want to not solder, they're probably a good way forwards, I would say. Yeah, cool. So we've moved this back. Let's get this in here and see how we are looking. Snap that to there. Oh, look at that. They're not even, they're almost touching. We could go back another degree here. In fact, we're going to do it. Because having those two touching, like having them share this little lip, is basically as perfect as we can get this. Because we want this gear to be as back and down as possible so that I don't have to modify the hammer arm too much and it doesn't touch and it still manages to do a full 180 degree swing. It's basically what I'm going for here. Face, solid, back by 1. Snap the motor. Snap the motor mount. Okay, those are touching, but not quite there yet. We're on the right track, though. So, is this working? Let me just double check here. Let's hide that for a second and make sure. Ah, you funny. That's not quite right. That's not centered on the motor. I need to make sure that's centered on the motor. But as it stands, it's too far away from where we want it. So we're going to do this again. Is this SolidWorks? No. This is 123D Design. It is software by Autodesk, who do make like Fusion 360 and stuff, but they stopped supporting this software a couple of years back. But if you have an install file, you can still run it. It still works. It's just that now, because it's not getting like security updates and patches and stuff, it does crash occasionally, especially I'm on Windows 10 right now. It crashes from time to time on Windows 10, one of which happened earlier today on stream, which is why I need to save. Yeah, so I quite like it because it works quite well with the way my brain works for CAD. And it lets me do... Whoa, definitely not 4. We want 2. Wait, no. I'm just going to try that all over again. Okay, that was the right direction. I want 2. There. Okay. Yeah, so it works the way my brain works when it comes to CAD. So what I'm actually going to do with this motor mount to make this line up properly. Now, first of all, we're going to double check this is the right motor mount for this motor. 11.8, that's fine for the 12mm that we've got here. But I'm going to just mod this a little bit so that the snapping works correctly, which is going to be done... unfortunately, a difficult way, because 123D is a little bit backwards in some ways. I mean, again, it's not a full CAD software package, really, because a lot of what you're doing is manipulating primitives, which is what I'm doing, like putting squares down and manipulating a thing. So I'm going to modify this lip ever so slightly. It's going to go down by 0.5, and then I'm going to put all this back together. So literally all I've done there is I've subtracted, or like I've split the one part into 3 so that the faces aren't connected anymore. And then I have moved those down so that when we do this, this face at the top here is just itself. It doesn't also connect to these, because when it was connecting to those, it seemed to be shifting the exact alignment of things a little bit, which I didn't like. So if we do this now... Nope, I didn't want to measure. I wanted to snap. There we go. That's better. But so if we do this now, and we actually have a look from the back here, we can actually measure this. Let's go between... no, actually we want to go... The trick here is to go between that face and this edge. 6 point... Oh, to the minus 7 millimeters. Okay. That's an interesting way to put that. And now I'm trying to find a direction where I can click the other side. Yeah, cool. So those are both exactly the same now, which is perfect. That is what I wanted to see. And that's why I modified this. So that is now sitting exactly where it needs to for this positioning of the gearing. And we can move it back even further. How far out did I move this in the first place? We've moved this back 6 degrees already. But I mean, it is like this was central over the motor, so yeah, we can move back further. That's cool. And in fact, again, we are just gonna straight up do that because I feel like that's gonna help out a little more. Man, I said I was gonna finish. I've said a couple of times that I'm like super close to finishing stream, and then I just haven't quite got the tweaking of this perfect. Again, so 2 more mil back. We're still not centered, which is fine. In fact, it's good. I don't really want them to go back to being centered, so... and here we go. We've gone too far now. But we've gone too far by probably 1. Like, this is double the distance I wanted it to be. Do I know of any other robotics events that aren't robotics, that aren't combat based? Yes. So Vesk, no, not Vesk. Vex Robotics. They do like robotics educational products. They do their own competitions, mostly aimed at high school and younger students. And then First Robotics is a kind of bigger version of that. And they use some Vesk products, but they build slightly bigger machines, and they do like robotics competitions as well. Again, I think they're more aimed at high school age students. I don't know. Yeah, I don't know how old you are or if that's applicable to you, but those are things that exist as robotics-based competitions that you can do if you are in the age bracket for those. If you're not, though, I know that both of those things are always looking for volunteers. They're looking for volunteers to, like, coach teams and help teams out, or, like, be there on the day and judge, or, you know, crowd control kids or whatever. Like, they're interested in having people around to help out. So that still might be a way in, although you wouldn't be competing yourself. It's still, you know, being engaged in a robotics competition and helping out, and, you know, getting some kids involved and interested in robotics, and potentially, you know, get them into engineering as a field or something along those lines. Okay. Well, that's interesting. Even 1 degree was not enough here, so let's just back those out and move this back again to where it was the last time. And then I think I will probably stop here. Once I've got this sorted, we will probably stop for today. Yeah, okay, that's perfect. That's beautiful. There's so little gap there. Yeah. I think that's ideal. This is exactly what we want, because we do want a little bit of gap so that the mount doesn't hit it per se. So that'll work. That'll be really good. And then we need, I'm just going to put another block in here and just check to make sure that we're going to get a full range of motion out of this thing. Also, that wasn't right. We want 12 by 12 by 10, right? Because that's what how thick is our thing here? I think it was, I did 12, didn't I? I did do 12. Okay, so this is the block that we need to clear the gears. And before we put that in, we're going to push-pull it out this way. Whoop. That's going to be our hammer arm, effectively. So that's in there. Look at this! Perfect! So that means it will definitely swing to there before the gears hit. In fact, it will swing, I would say, half a degree to a degree further forwards. Beautiful! That is what I like. Yes, okay. This is our gear stack up. 30-to-1 motor, 20-tooth gear, 10-tooth gear, exactly this arrangement. That'll work. And also, I'm going to have to move things around because now I'm going to have wiring safety out here. I'm probably going to have to put the Malinky up front, maybe, because at the moment there was a Malinky out the back, but that's going to get mushed under these gears. So we're going to have to move some things around in the design. But for now, this will work. I will finish this off as a little test platform. I'll do some test prints. You will see all of that in a video in a few weeks' time. Yeah, this has been fun. This has been an interesting, slightly confusing experience trying to get this all to work and get the gearing right and get things the way I want them to, but I think we're getting there. And I think after some testing with a test platform, we will be even more there. But hey, at least you now know where things are going with this, and you know, you'll have a leg up if you watch this and then watch the video that comes out in 2-3 weeks on building Squeeky version 2. Anyway, that is going to be it for this stream. Hope you've enjoyed that. And remember, tonight, Dual Spinner Multi-Brain video, the Vert this time, fight report. So yeah, it's an interesting one. You're going to want to see that. And I will see you next time.